Let's talk about calculating volumes using cylindrical shells. When we calculated volumes by slicing the disk method or the washer method, we always sliced our solid perpendicular to the axis of rotation. And I just wanted to point out that slicing, disk method, washer method, all three of these are section 5.2 type situations. Okay. When we use when we calculate volumes using the shell method, we always slice our solid parallel to the axis of rotation. So this is the exact opposite of what we did earlier. Before we did perpendicular, and that was for slicing, disk, and washer methods. But when we do the shell method, we want to go parallel. All right. So why don't we take a look at this picture down below over here. In this picture that we have here, we are rotating about the y-axis. Okay. And what we're going to do is we're going to chop up parallel to the y-axis. So we chop up parallel to the axis of rotation. In this picture, I've indicated that that axis of rotation is the y-axis there. So we chop it up like this, and then we just want to look at one thin slice over here. And when we rotate that thin slice about the y-axis, we get something that looks like a cylinder, a circular cylinder, but it has a little bit of thickness. So we call this circular cylinder. This is a shell. Okay. And if you look at this picture we have on the far right, this is a whole collection of shells. So this is a collection of shells. All right. And this collection of shells becomes a good approximation for the actual volume. So when we work in this situation, we first need to figure out what is the volume of a shell? What is the volume of a shell? And how are we going to figure that out? Well, watch. We're going to take this shell, which is like a circular cylinder with a little bit of thickness over here, and we're going to cut it open, and we're going to unroll it. So one thing I want to do is I want to label this point right here. This point right here, the x value is going to be what we call x sub I star. And the y value is going to be given by the height of the function. So that's f of xi star. That's what that point is. And the star just means we're somewhere inside this really thin interval over here, that little bit of thickness. So when I unroll this object, I'm going to get a rectangle, right? So this is a rectangle. And when I look at this rectangle, we can see that this rectangle here has a little bit of thickness. And due to the way that we constructed things, this little bit of thickness, in this case, that lies on the x-axis. So that's why we have this dx here. So when we want to calculate the volume of this shell, we're going to have to multiply three things together. We have a rectangular slab here. So the height of the rectangle is going to be given by the height of the function. The width of the rectangle that's really going to be given by 2 pi times xi star. So this comes from the circumference of a circle. Okay. So basically, we're going to multiply three things together. We're going to take the circumference of the circle times the height times a little bit of thickness. And we multiply those three things together, that's going to give me the volume of this shell. So if I scroll down a little bit, we could see that we're going to have the following. The circumference of the circle is going to be 2 pi r, where r is the radius. But in this particular case, our radius is given by the xi star. So that's going to be equal to 2 pi times xi star, like this. The area of the rectangle is going to be 2 pi r, which is the circumference of the circle, times the height of the rectangle. So that's going to be equal to 2 pi xi star times f of xi star. Okay. In the thickness of the shell, that's going to be given by delta x, as we highlighted up here. So when I put all of this together, we get that the volume of a single shell is going to be 2 pi times xi star times f of xi star times delta x. So we can really put all of this together to get the formula for a volume of a solid of revolution. So our volume is really going to be the limit as n goes to infinity. We're going to add up the sum of a bunch of volumes of shells. So we're going to start off with n shells, and then we're going to let n go to infinity, and that's going to give us the true volume. So our approximate volume is the summation from, as I goes from 1 to n, 2 pi xi star times f of xi star delta x. And at this point, we should be familiar with the idea that this is the formula of a definite integral. Sigma is the Greek letter for s, so we put a giant S here like this. We're going to have a 2 pi x times f of x dx, and our x values are going to range from a to b. Okay, so let me highlight this. Our volume is really going to equal to this integral, and I will maybe write a more refined formula in the next video, and we'll do an example. All right, everyone, take care.